I haven't said anything yet, so don't apply yet. All right, come in, sit down. Hurry. Welcome to Voxxed Athens. This is my first time here. I'm very excited. There's a ton of people, which is surprising, because usually when I talk about compiler stuff, there are like 20 people in the room, because it's compilers. So this talk is sure about compilers, but more about the machine learning part, right? So my name is Chris. I work for a tiny little company that you might know. And the most important question of the day, and probably of the whole conference, is, and I've never asked this question in Greece before, so who in this room has a Twitter account and is using it? Oh, hands went down. What the hell? It was like half of the hands came down. So if you don't have an account, I want you to create one. If you have one and you're not using it, reinstantiate it, because I want you to tweet about the event, right? I'm not sure what else you do. I mean, take a picture of and then post it on Instagram if you really want to, but Twitter is where the whole IT industry happens, right? All of us, the speakers, we're all on Twitter. So if you have a question to any one of us, tweet us and you'll get an answer. So please tweet about all the sessions you're going to see, all the sessions you like. As I see, all these sessions are being recorded, so let other people know what they're missing, so they're here next year, or they watch it on YouTube. If you're going to tweet about my talk, add the hashtag #TwitterVM team, because Twitter actually has a VM team. So we are not so small anymore. We are now about 8 people, I think, and we have 3 GC engineers. I don't know if you know people who used to work at Sun and Oracle. We have a Greek on the Twitter VM team. His name is Tony Prentices. I think that's how you pronounce his name. I don't even know. So even that, 3 GC engineers to take care of all the GC issues we have and everyone in the world has. I'm a compiler engineer. I do compiler stuff. So I work on, the chit compilers and Graal and so on, and do fun stuff like this, go out and tell the world the cool things we're doing. We have a bunch of people working on infrastructure things, nightly testing, blah, blah, blah. We build our own JDK, so we have to do that as well. And then we had, unfortunately, we just lost her, she worked on AUTOTUNE. And AUTOTUNE is the tool that I'm going to talk about today. All right. So this is me, if you don't know me. I'm working on JVMs for over 14 years now. And all these 14 years, I'm working on JIT compilers. So I'm going to ask you a bunch of questions because there are many people in the room. And I want you to really raise your hands now. Do people know what a JVM is? I mean, it's a stupid question, but, OK, so I'm not going to explain that. People know Hotspot, the JVM of OpenJDK? Yes, so Hotspot. Do people know, who knows what a JIT compiler is? All right, much less. So let me explain that real quick. When you compile your Java code or your Scala code or whatever down into a class file, into Java bytecode, what the JVM does, it takes that class file and then runs it. First, it interprets it, and that's really slow. And then the JVM on the fly, during runtime, compiles it into native code, just in time. These are just-in-time compilers. Unlike AOT compilers, like GCC, where you ahead of time compile, you just watch Quarkus and native image and substrate VM, that's AOT, right? You compile it before you get a native executable. Just in time, you compile while you run. That has a bunch of advantages because you have actual real-world live runtime data, like profiling data and so on. So I work on JIT compilers. I used to work at Sun and Oracle in the Hotspot compiler team. So I was mostly working on C2. Hotspot has 2 JIT compilers currently. Who knows C1 and C2? Right, 5 people. Good. So C1 and C2, there's a JIT compiler called C1 or client compiler, and there's another one called C2 or server compiler. If you're kind of a little bit older already, you remember -client, -server. We used to use that years and years ago. Don't do that anymore. You don't need it. The purpose of C1, it's a high throughput compiler. So the purpose is to get away from interpreting code as quickly as we can to run on native code, right? It doesn't do a lot of fancy optimizations, just the bare minimum to get onto native code. And then C2 is a highly optimizing compiler. So it uses all the profiling information that we're gathering while we are running and then produces peak performance code. That's basically what you're running on, right? All right, so I was working on C2, major pain in the ass. These 3 projects are the biggest ones that I've worked on at my time at Sun and Oracle. JSR 292, Invoke Dynamic, you might know that. If you're using Java 8 lambdas, you're basically using Invoke Dynamic under the hood without you knowing it. That's how it's implemented. There were 2 implementations of JSR 292. The first one was a lot of handwritten assembly code, like pages and pages of assembly code. It was a major pain to maintain, major pain to write in the beginning, and then we also had to port it to all the architectures that the JDK supported, right? And then on top of it, after a while, we figured out that we actually had a performance issue, so we redesigned the whole thing and moved a lot of that handwritten assembly logic into Java, into a package called Java Lang Invoke. So that's where it lives today. A lot of that Java code I wrote, so if it doesn't work, you could technically blame me. But I always say the code I wrote was perfectly fine, and people touched it after me, they broke it. So Chap 243, Java level JVM compiler interface. We introduced that interface in JDK 9. So basically, yeah, let me ask that question now. You just saw a talk about Graal VM, right? Who knows what Graal is? Not Graal VM. All right. So most of you just saw a talk about Graal VM. There were like 6 hands up. What did you? So Graal is, okay. Graal VM, let's start there. Graal VM is a marketing term for 3 different technologies. Graal, the JIT compiler. Who knows what a JIT compiler is? I just explained it. All the hands should be up. It's like, what am I doing here then? God. So Graal, the JIT compiler. Then Truffle. Truffle is a framework to implement language runtimes. And then Substrate VM. That's what you just saw, right? Substrate VM, native image. Okay. So Graal, the JIT compiler, is a replacement for C2, right? The compiler I just talked about. And Graal is written in Java, right? So what we did with Chap 243, since Graal has to talk to Hotspot, and Hotspot is written in C++, there is an interface, right? There's a little bit of JNI interface, obviously, but there's also a Java interface, like a real interface. And so we extracted that interface that Graal was using, put it in a module, and now we have it. It's not really an official API. It's also not a supported API or anything, but it's stable-ish, so it doesn't change a lot. That means since 9, 10, 11, 12, 13, basically you can compile one version of Graal and then use it with all these JDKs. That was the purpose of it. And then Chap 295, we did 243, 495 ahead of time compilation. This is not native image. It's not the thing you just saw. This is something completely different. It's basically a small command line utility that takes in class files or char files and then compiles all the methods that are in these classes with Graal and spits out a shared library at the other end. And then Hotspot can pick up these shared libraries when it starts up. It can help with startup performance improvement. Basically, it can improve your startup if your application is very big and runs a lot of different code, because basically you're avoiding to interpret a lot of code. It helps, but not a lot. Yeah, the difference between this one, ahead of time compilation, and native image is this one is actually Java, while native image is only a subset of Java. Remember that. And now I work for the greatest company on the planet, which all of you are using as of today. This is Twitter. That's what it looks like. So we have hundreds of microservices, right? And we have thousands of instances of these microservices. And then on top of it, we run on heterogeneous hardware. We own our own data centers. We own our own hardware. We know what machines we have. But even we run on heterogeneous hardware, right? You guys, you run in a cloud. You don't even know what you're running on, right? So in general, performance optimization, hand tuning doesn't scale, right? Most important thing. So performance optimization today works like this. You sit at work and you're annoyed by the performance of something, and then you decide, okay, fuck it, I'm going to tune it, all right? Then you tune it, blah, 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 and then you're done and you're happy probably with the result. You do this every 3 years, 5 years, never, right? That's the problem. And then you can only handle a few parameters because you have to build up a mental model in your head to do this. It's very time consuming, labor intense, error prone, you can make mistakes, but upgrades make optimality fleeting. That's the important one, because we all live in this super agile world today, right? You all are super proud that you deploy hundreds of times a day, because it's the cool thing to do. We also deploy multiple times a week for some of our services, but the problem with that is the code is constantly changing, right? If you tune for the code you have today, the code will be different tomorrow, right? So, very important, many services operate below optimality. That's certainly true for all the Twitter services, right? Because we're in the same boat as you right now. Because what I'm talking about today, this is not on in production yet. So everything that runs today runs below optimality. Could run way, way better than it does. A little bit of theory here. So performance tuning, what is it? It's a function defined over domain X. And what you want to do is you want to find a configuration that maximizes F, whatever F is for you, right? It could be throughput, it could be to reduce latency, it could be to reduce memory consumption, it could be to reduce CPU utilization, whatever it is, right? And then it's always subject to some constraints. And the number one most important constraint is it still has to work. And you will see later that you can actually tune it too far. You can tune something too far so it doesn't work anymore. With the experiments that I did, you will see that. This is what performance tuning looks like, basically. You pick a parameter to test, then you run it on the system, whatever you have, right? You measure your F, and then you take that F, and you, a performance engineer, a person who is highly paid, I hope at least, has to decide if what you just got, the result is better than before or not. And based on the outcome, you have to decide which value to try next. That's what performance tuning is, right? So the performance engineer is certainly overkill here. Maybe we could try to use a monkey to do it, but what we really want is some black box. We don't care what it is, right? The only answer we need is my results measurement, is it better or not? That's all. And for this black box thing, we use something called Bayesian optimization. And Bayesian optimization is a method to learn, potentially noisy, that's important, objective functions iteratively efficiently. We need an answer quickly, right? We can't wait months and months to get an answer because, as I said, code is constantly changing, so we need an answer as soon as we can. And this one does it. Finds near optimum in a few iterations. Works well with nonlinear, multimodal, high-dimensional functions. That's the important one. Because the JVM has hundreds of parameters to tune, right? You could tune all of them if you wanted to. Sometimes I get the question, so can I tune my database? Well, of course you can, right? I mean, the JVM here is just an example. You can tune whatever you want. Tune your Minecraft if you want to. So my colleague Rumpke, if you want to know more about this machine learning part, Bayesian optimization, the whole theory behind it, he knows it. He has a very soothing voice, much nicer than mine. So listen to his talks. He gave a talk at Devoxx about 2 years ago where he explained all this. And you see the slides that he's using. All I did was I stole his slides. And so I'm going to explain to you really quickly now, very roughly, how Bayesian optimization works so you can better understand all the graphs and data you'll see later. Okay. If you know Bayesian optimization, don't ask any questions. Okay, good. I'm glad that's out. So we have a parameter that affects performance from -6 to 6, and then on the y-axis we have performance, highest, better. And these are actual 3 data points we got from evaluations. So these are real results. This is the real performance curve. which we don't know, right? Obviously we don't. So what Bayesian optimization does, it just assumes a curve. It looks like this. And then the blue part above and below the curve is the uncertainty, right? You see where we actually have data points that the uncertainty is 0 because we know, yeah, that's correct. So overlaid with the actual curve looks like this. It's not really the same, but it doesn't matter because over time, it will figure it out. So the next what it does, it puts in a line with the best result you have, and then all the blue part above the red line, that's the bottom curve. That's the expected improvement. The more blue you have, the more expected improvement you have at the bottom. And then it tries the best one at the bottom. That's your next value that you're trying. So we try this one, we run it, we get this result. Then we try this one, we get that result, and then the one to the left, we get that result. And then this one, and then we've exhausted that space over here, and we know the curve of the graph, right? And then we just keep going. We take the one on the right over there. Yeah, that wasn't good at all. We take the one on the very left. Wasn't good at all. And then over there, we do this one. Yeah, much better. So we keep going. This one, this one, this one. And that's the global optima. That's what it does. That's what you would be doing as well as a human. But the machine learning, the Bayesian optimization can do it so much better and so much faster. All right. So we like Bayesian optimization. Again, non-parametric, robust, extensible. The last one is the important one. Battle tested on many types of real-world high-impact problems. So we know that Bayesian optimization works. This is important because we are not there yet, but that's the goal of this whole project here, that we will have AUTOTUNE always on in production. We want all of our hundreds and hundreds of microservices to tune themselves always by themselves, right? And then we need to make sure that what the technology we're using actually gives us a result that is valid. So that's why we like this guy. Okay, that was it. Now we're talking about numbers and graphs, the important thing, at least I think so. So what is AUTOTUNE? I call it Bayesian optimization as a service. It's a BOAS. If you have a Twitter account, get that hashtag trending. I try it at every conference, never works. BOAS, get it trending. Our Bayesian optimization is something called WetLab, which is a company that we acquired a couple years ago. And WetLab is just an enhancement of a framework called Spearmint. And Spearmint is still available on GitHub for free, open source. WetLab, unfortunately, we cannot open source some IP in it that we're just not allowed to. So that's one part. It actually, I mean, this is kind of a joke, but not really. It's actually really a service running inside of Twitter that other tools talk to for other Bayesian optimization things. And then AUTOTUNE is really just a driver to run experiments, right? Think of it as a complicated shell script that starts and stops measurement instances. That's really all it does. Sounds simple, is of course not, right? Because you have to start and stop instances in your data center and blah, 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 and has to talk to a bunch of things, so it's not that easy, but that's all it does. If we are going to open source AUTOTUNE, and we will at some point when it's actually usable, and it has a user experience that's much better than it is today. Don't ask me what it is today. Someone could take it and make it work with Spearmint, right? And then it depends. We run in Aurora on Mesos, for example. But if you run on Kubernetes or Docker or whatever you want, you would have to write, let's call it a backend to start and stop instances, right? That's all you need. And then you could do the same thing. What is Graal? Java Virtual Machine Just-in-Time Compiler. Everyone should be able to explain it to me right now. Actively developed by Oracle Labs. There's an official OpenJDK project for it, but all the work is done on GitHub, actually. Uses JVM CI, as I said earlier, written in Java. The part that it's written in Java is not important for this talk, but if you're interested in trying Graal, the JIT compiler, at your company or for whatever, you should watch this one, Graal, how to use the new JVM JIT compiler in real life, because it explains to you the differences between a JIT compiler that's written in C++, like C2, and Graal that is written in Java. No, there are basically two differences. They're still true today. We are Oracle, the JPG, Oracle and Oracle Labs are working on, let's call it fixing the issue. It's not really an issue. But there are two things as of today that you should know. Number one, it's written in Java, so that means we're not AOT compiling it yet. That means it has to compile itself. It's called bootstrapping, and it adds a little bit of an overhead to your startup, but it's very, very small, and I'll show in this talk that it's basically you can forget about it. And then the other thing you should know is that when the JIT compiler does compilations, it uses memory. C2 allocates memory with malloc on the native heap, while Graal allocates memory on the Java heap. You just have to know about it. If you know about it, no problem. If you don't know about it, you're like, oh my God, what the hell's going on? Okay, so which parameters did I tune? I picked 3 inlining related parameters. Who knows what inlining is? Okay, we're explaining this. So if you have a piece of code that it's repeating in your code, what you do as an engineer is you refactor that into a small method, right? You're supposed to do that, it's easier to maintain then, obviously, but from a performance perspective, that's not a good idea. So what the JIT compiler does, or many other compilers do, it basically undoes what you did. It takes that tiny little piece of code and puts it back at all the call sites. The reason it does that is, number one, we don't have to call it. We don't have to pass parameters and shit. But the more important thing is that the compilation unit, our worldview gets bigger. When we see more, we can apply more optimizations. So inlining is called the mother of all optimizations because it enables other optimizations to work better. Most notably, something called escape analysis. So I'm not going too much into detail, but escape analysis can get rid of object allocations when the compiler can prove you don't need it. The more the compiler can see, it's easier for the compiler to prove you don't need it. Right? Okay. So I'm tuning 3 inlining related ones. The first one is called trivial inlining size. It has a default value of 10, and 10 means 10 nodes in the compiler graph. So every compiler parses source code into a graph. Let it be, I don't know, C++, or in our case, Java bytecode, that's our source language. It parses it into a graph, and if the graph has less than 10 nodes, we inline it always, because we know it's a very small method, it's trivial. Okay. Maximum inlining size is the other end of the spectrum. If it's more than 300 nodes in the compiler graph, we don't inline it. Small compiled low-level graph size, 300, is pretty much the same as the second one. The difference is pretty much every highly optimizing compiler has 2 or more levels of intermediate representation of types of graphs. So there's Graal and C2, they have one that's called high-level intermediate representation and low-level intermediate representation. The difference is the high level is high and the low level is low. Understand? Okay, good, very nice. That's how I explain things, right? And everyone thought, oh yeah, oh, he's right. So, no, kidding. The high-level one is closer to the source language. Right, in our case, Java bytecode, while the low-level one is closer to the actual machine instruction for your architecture. In our case, x86, but could be Spark or ARM or whatever, right? So these are the differences. It also has a default value of 300. I'm still doing that talk, actually. There's a talk called Twitter's Quest for Holy Grail Runtime. It basically tells the story of me working the first year at Twitter, how we started running services on Graal, what bugs we found, and so on and so on. And I'm also, the most important thing of that talk is I'm showing how much user CPU time we're saving by using Graal. And one thing I'm doing during this talk is what I told you earlier to not do, I hand-tuned. Right? I sat down a Friday afternoon, a couple hours, and I hand-tuned these 3 parameters you just saw because I wanted to see how much can we get out of Graal more than what we already get by default. I did this before I did all the AUTOTUNE experiments. So if you're interested in that, watch it. I just took out 2 slides of this talk, and you can see at the bottom there's still JDK 9 in there, so I made these slides a while ago. JDK9, the Java no one ever used, right? So we're comparing blue C2, orange Graal, and then the purple one is the experiment. That's where I hand-tuned the parameters. By just running on Graal, the numbers are really fucked up, I have to fix this. By just running on Graal, we're looking at GC cycles here, sorry. We're looking at GC cycles here. We reduced by 2.7% by just running on Graal instead of C2. So 2.7% less GC cycles. And then I hand-tuned it, and I got another 1.5% less GC cycles out of it, which is great. It's not a lot, but remember, this is the tweet service. It's still serving the same amount of tweets, millions of tweets per day. Does the same amount of work, and remember, GC cycles always affect your latencies. So if you have less GC cycles, your latencies are generally better. And then, this one is the one I care the most about, user CPU time. Because if we can reduce user CPU time, and we have thousands of instances of something, we can save a lot of money by doing this. So by just running on Graal, as you can see here, we reduce CPU utilization by 11%, which is ridiculous. If you ever worked on a compiler before and you did some performance optimization work, you will never get 11, like impossible. And then by hand tuning, I got another 2% out of it, which I was very proud of. I thought that's pretty cool. I probably had a beer that night. I'm not sure, can't remember. But this is a lot of money we are saving, right? Okay, 2%. Remember this. I'm very proud of it, but you will see that AUTOTUNE kicked my ass. So this is a snippet or snippets out of the configuration file. I gave my parameters that I'm tuning actual ranges. You can do that, and you don't have to, right? You can say from 1 to 1 million or whatever, because you remember the way Bayesian optimization works, it will figure it out itself anyway. But I gave it ranges for mainly one reason for this talk. I needed this to finish in a certain amount of time so I can fit it on a slide for you to understand. Okay, that's why I gave it ranges. And I know the service really well, so I know what ranges are good ranges. Okay, but you don't have to. Test setup. If you're doing performance evaluation, it's very important to have a good test setup. If you're expecting single-digit percentage performance improvements, you need dedicated machines. If you're running this in your data center or even in a cloud, right, you don't know who else is running on your machines, right? If you have a noisy neighbor or whatever, it will completely destroy your results, and all your results will be in the noise. You can't tell anything. So I have dedicated machines. All instances receive the exact same request. It's very important. Not only the same number of requests, but the exact same request. Imagine the tweet service. A tweet could be 1 character long or 280 characters long. And the memory allocation pattern for the 2 tweets would be very different. But we want to compare apples to apples, so exact same requests. And these requests are real-time requests that are coming in. So it's not a replay or anything. I just run, if I would run it now, it's basically the stuff you're tweeting right now. That's what it's serving. I run this JVMCI version, this Graal version, not that important. Default tiered C1 Graal setup. Who knows what tiered compilation is? Tiered compilation, yes, okay, a few. So remember when I was talking about C1 and C2, that there are multiple compilers? So what happens is, you run your application in your JVM, then you start out interpreting your code a little bit, then we compile with C1, and we compile it in a way that we compile in additional code that collects profiling information. It collects how often was a method called, it collects how often was a branch taken, how often was it taken, and we collect types. And then, after a while, we recompile with C2 using the profiling information. So we are stepping through the tiers. Pretty much every JVM as of today does that. It's the most powerful thing to do. All right, so basically what we do in this tiered setup, interpreting C1, C2, we replace C2 with Graal. We still run C1 and all that stuff, we just compile with Graal at the top. Experiment 1, the tweet service. My favorite service. It's a Finnagel thrift service. Finnagel is one of these frameworks that we use to build our microservices. It's open source. It's an extensible RPC system for the JVM used to construct high concurrency servers. I have no idea what it is. I really don't. No clue. The only thing that is important to me is this: it's 92% in Scala code. The way most of our finagle-based services, most of our services actually look like, we use Netty, then finagle, and then the logic of the service. Right? That's kind of what they look like. This is our objective, what we are trying to improve, our F, if you remember. And here at the end, you can see we want to improve user CPU time. So we want to reduce user CPU time. And you remember that Bayesian optimization always looks for a maxima, right? So since we're all very smart computer scientists and super good at math, we can solve this problem by saying 1 divided by. Amazing. And this is our constraint. I only used one constraint, and in this particular case, it's something called throttled. Mesos does that to you if you're using too much CPU and you're a nasty, you're a nasty citizen. Then it says, "Oh, you're throttled," and it kicks you out. When we have, in the future, when we have this AUTOTUNE always on in production for all of our services, we need certainly more constraints. Every service owner has a bunch of metrics where he knows his service runs fine, right? All these metrics they are using should be in here. I just didn't have the time to do it, and I know that this one is fine. I was monitoring this run very closely, so I knew what the hell was going on. But if we have it on for all of our hundreds of services, we can't monitor them, right? We have to trust the constraints. All right. That's the run. That's it. That's the tweet service for 24 hours. And you can see we're looking at blue, the experiment, and orange, the control. And as you can see, this is requests per second. They are the same. They should be the same. And you see these slices. They are 30-minute evaluation runs. So we run an evaluation for 30 minutes. It's rather short, but 30 minutes, again, same reason. I wanted this to finish in a day, to put it on a slide. And I know the service compiled everything in 30 minutes and comes to a steady state, so I could do it. This is the outcome. That's user CPU time. You can see if the blue line is below the orange one, that's an improvement. The spikes you're seeing are the restarts of the JVM. That's basically JIT compilations. When we compile all the shit, then the CPU spikes up. And then what AUTOTUNE gives you is a web page that has a table with results on it. And it's sorted by objective, and the top entry is 1.0838, which means that we reduced user CPU time by 8.4%. You remember the 2 that I got? So very proud of 8. Shit. So much better. 8.1, second one, then a 6.4, another 6.4, 5.8, right? So let's assume the first 2 are outliers. So we could probably expect a 6.4% improvement in the real world. The bottom of the table looks like that. And I'm showing you this because you see 3 actually violated the constraint. So we tuned too far that we got throttled, something went wrong, and it kicked us out. So as I said, this actually can happen. And then we can look at the charts of the parameters we tuned, and these are the charts, but take it with a little bit of grain of salt, because every data point in this chart depends on 2 other values, right? In our case, we're tuning 3 parameters. We're exploring a 3-dimensional space. It's very hard to put on a slide. So every data point in here depends on 2 other values that are not the same. Okay, but it gives us a little bit of an idea what the trend is. You can see there is a trend upwards, right? Default is 10, our best result is 21, and then when you look at the curve a little bit, it probably is 21, 22, 23-ish. That's where our maximum is. All right, this one doesn't actually make that much difference, right? It's rather flat. We have the 2 outliers at the top right, but again, remember, they might be outliers or not, because it could be that just paired with the other 2 values that they are using, it's just a very good configuration, right? But it doesn't matter to us. We don't need to know, because we just take what we get. right? We take ever the best result we get, and then we take that. And this one, it's very obvious what's going on, right? This one affects performance a lot. The default value was 300, and our best result is roughly the 600 mark, right? So it should be twice as much as the default is for this particular quote, for this particular service. So the next thing I did was I did a verification experiment. So I took the best result that AUTOTUNE gave me and ran the tweet service for 24 hours with these values. So again, blue C2, orange is Graal, the default version, and then red is Graal with the values we just found. This is just requests per second. This is the GC cycles graph. So P is scavenge cycles because it uses parallel GC. By just running the tweet service on Graal instead of C2, we reduced GC cycles by 3.4%, which is great. Believe me, it is. And then we tuned it, looks like that, and you can already tell it's the same. So we improved performance by 100%. No, we improved the improvement by 100%. Let me not misspeak here. Up to a total of almost 7%. So 7% less GC cycles is a big deal. This graph, this graph is the same data, just visualized differently. Maybe some people can understand this better. It's basically how many bytes did we allocate per tweet. And as you can see, over the 24 hours, it's pretty flat. It has little fluctuations because tweet length are important, but it's pretty much the same. And of course, the improvement is the same, right? Because same thing, you allocate the memory and then you GC it, same thing, right? That's the one I care the most about, user CPU time. And in this particular run, you've seen it kind of before, it was 12%. So we can use 12% less machines to serve you all the tweets you want to see, right? And then we tune it, it looks like that. It's another 6.2, up to a total of 18.2%, which is ridiculous. Right? 18% less machines. Imagine how much money that is. Imagine how much less electricity, how much less cooling that is. We're trying to save the world here. Are you with me? All right, good. So then I was also looking at P99 latencies, and I was looking at only 2 nines and not 3 or 4, because if you look at 3 or 4 nines, you're only looking at your longest GC, right? That dictates your P49 number. If you look at the 2 nines, you kind of get a rough idea of the world, what it really looks like. So there is certainly an improvement in the latency times when we run on Graal. It's a little hard to tell how much it is. This is AUTOTUNE, also certainly better, a little hard to tell how much it is. So what I did was I integrated over the 24 hours, looks like that, and then we can tell how much it is at the very right. By just running on Graal, not only are we reducing CPU by 12%, we also reduce P99 latencies by 20%. And then we tune it, we get another 8 to a total of 28% less P99 latencies, additional to the 18% less machines. So what that means is that you get your tweets 28% faster. It's incredible. If you would be scrolling really fast in your app, you could read 28% more tweets, right? That would be great. I would appreciate that, by the way. Would bring stock price up. Good. So let's do another experiment with a thing called social graph. And the reason I'm doing this, social graph is also a finagle thrift service. Same thing as I explained, Netty, finagle, just different logic on top. The reason I'm doing this one is to show you the difference, what outcome you can have. So this one is an abstraction for managing many-to-many relationships at Twitter. It's basically who follows you and who is following you. That's what social graph is. Good. Same objective. We're trying to reduce user CPU time. You've seen all this before. Same constraint. Not going to talk about that again. And that's the run. Same thing, different day. You can see like the curve is different. Blue experiment, orange control, 30-minute evaluation runs, same thing. That's the outcome. Certainly improvements and also runs that are way worse. And here's the table. Good. The best one here we have is 7.6. It's already great. 7.6, I'd take it if I can get it. There's another 7.6, a 7.2, a 6.8, a 6.4. when we look back to what we got with the tweet service, you know, the first two we thought could be outliers, and when we expected a 6.4-ish, what we got in the end was 6.2, if I remember correctly, right? So it was pretty close to what we actually got in the real world. So let's say the 7.6 are outliers. Let's hope for a 7% improvement. That might happen. Bottom of the table, one constraint violated, sorry. Not much else to see. The charts, similar to what we saw with the tweet service, maybe not as obvious. The best one we found, again, was around the 23, right? Before it was like 21, so that they're kind of similar. This one, a little tendency upwards, you could say, maybe, right? There are a couple outliers at the top, but down there we have a slight tendency upwards. This one, also a tendency not as clear as with the tweet service, but certainly up. And the one thing to point out in this chart is, if you look at the best one, it's roughly 650. I'm not sure if you paid attention, but 650 was my range. So for this guy, maybe if I run it again with a higher range or no range, I'll get a better result. Okay, so verification experiment, we've done that before. This is what it looks like. The social graph service uses CMS, so we're looking at par news cycles, and the improvement by running on Graal instead of C2 is only 1.6%. If I can get 1.6% for free, I'll totally take it, right? And then we tuned it, and that's the important thing, and you might already see it. We tuned it twice as much as we get out of Graal by default. That's very important, because that's the money we throw out the window, because we don't tune. Yeah, sure, we get a little bit of improvement with Graal when we do it, but we get twice as much if we tune it. So 5% up to total. User CPU time, we get 5.5, which is roughly half what we saw with the tweet service, so that's what I wanted you to see. It depends on the code, on the logic you have, how much can be improved, right? And the thing to note as well here is, this is roughly half of the tweet service, and also the 1.6% was roughly half of the tweet service. So the CPU and the memory allocations we can save, they kind of go hand in hand, all right? So this is AUTOTUNE, looks like that, 7.8 to a total of 13%. So again, we tuned more out of the compiler than it gives us by default. The thing to note here is, some people might notice, when you look at the blue and orange line, it's basically the improvement is the same if the load is low or the load is high. But for the AUTOTUNE result, it's actually lower here than when the load is high, which is odd, and that should not be the case, and I didn't have time to look into why that's the case. But it's not a big of an issue, because we don't care too much about the improvement when the load is low, because we size our instance sizes by when the load's high, right? That's where we need all the improvement. So again, same thing, money thrown out the window. Questions? Anyone a question? Everyone, 3 people. Is this your question? No.
We have a question at the back.
No, we're not. We're doing questions later. It was just a joke. Oh. So the question should be, yeah, well, cool. I mean, this is all very nice, and you're praising Graal so much. Did you do the same AUTOTUNE experiment with C2? And the answer is, well, of course I did, right? I couldn't come up here on stage and not have done that, because that would be stupid. So we did the same with C2, because remember, this is actually an AUTOTUNE talk. I know I'm talking about Graal a lot, but it's an actual AUTOTUNE talk. I picked 3 parameters, C2 parameters, that are similar to the ones that I tuned for Graal. The first one is called max inline level. Graal doesn't have that, okay? So max inline level, default value of 9, means how deep inlining goes, right? So how many levels are we doing inlining until we stop? It's very important these days, because everyone's using thousands of frameworks, right? Framework A is calling, framework B is calling, framework C calling, and then we're done at 9. Maybe we were not even at the code that you wrote at that point in time. So we picked 9, I don't even know when. I would have to go back into mercurial history, but we picked 9 at least 10 years ago, right? Source code 10 years ago was very, very different than today. So 9 is certainly not high enough for all the code out there, unless it's 20-year-old code and never been touched. Max inline size is the exact same thing as the one with Graal. The difference here, the 35, is bytecode size, right? With Graal, it was nodes in the compiler graph, but here it's bytecode size. If you ever added a search statements to a small method in your code, and then suddenly your performance went to shit, it's because of that guy. Because if you add a search statements, it adds to your bytecode size, right? And then it becomes bigger. C2 doesn't discount for assert statements when it looks at code to inline. No, it's very embarrassing. We never fixed it. I'm very sorry. Use Graal. Inline small code is an odd one. It's 2,000, and it's 2,000 bytes of compiled code, of native code. I'm not sure who added that. I found it odd. I think the rationale behind it is if you looking at a method to inline and you already have compiled code for it and it's very big, it probably increases the size of your method as well. It's kind of weird to think about, but I can understand to some degree. The weird thing about this one is if you're looking at the method to inline, it's obviously is very important to you to inline it, right? And then if you inline code, it can actually reduce the size of your compiled code. Because if you inline more stuff, it can collapse things, remove object, all the things. So it's there. If you run on C2, you have it. Same thing, I gave it ranges for the same reasons as before. And this is the run. I used the tweet service in this particular case, 24 hours, 30-minute evaluation runs. Nothing more to say here. That's the outcome. You can see what the hell's going on, but here you can. All right, so the best one we have is 5.1, which is great, 5.1. Then we have a 3.8, a 3.5, a 3.3, and a 3. Okay, let's assume the first one is an outlier, and let's be nice to C2, and let's say we get a 4% improvement. That would be very nice. For a compiler that's at least 15 years old, we're not really touching it anymore, and it has been tuned and optimized the hell out of it to run all the Java code in the world the best it can. A 4% improvement is really good. The bottom of the table looks like that. Not a lot to see here. No constraint was violated. Sure, why not? These are the charts. That's the max inline level thing I was talking about. I mean, everyone can see what the hell is going on, right? So 9 is not enough. It should be 16, 17, 18. That's what it should be for this particular code, but I'm arguing for all the code out there, right? So if you want to get into performance tuning and compile a little bit, start with that guy. That's max inline size, which is completely flat, right? There's this one outlier that's our best one, but otherwise it's completely flat, which surprised me because the trivial inlining size for Graal affected performance a lot. And here it doesn't. And this one, yeah, not a big surprise. That doesn't really affect performance at all. I didn't do a verification run for C2, but let's say we get a 4% improvement, as I said. Very nice, very good. I'm sure all of you would take a 4% improvement. But compared to what we get with Graal, it's just very small. Because with Graal, with the tweet service, we get 12 and then an additional 6, 18 compared to 4. Sure, we are running Scala code, it's slightly different, but the main point here is Graal as a compiler technology is much more suitable going forward to build new optimization techniques. So the summary of my talk, and I have the same summary for all of my talks, it's this. And the reason why I'm showing you this is I want you to try Graal. There are some reasons I want you to do this. Number one, I didn't talk too much about how much money we're saving, but just the tweet service right? If you look at the tweet service, the improvement we got from the tweet service, the savings alone from the tweet service per year is more than I get paid. I mean, I'm not sure how much you get paid, but it's more than I get paid. So, I'm a very nice guy. I want you to save money too. Because next year when I come back, right, and then you use Graal and you save some money, and then you say, hey, thank you so much, I'll buy you 2 beers and you can sleep in my house. That's basically what I want. I want friends around the world. So, Airbnb is too expensive. So, I'm joking here, but only half, right? Sure, save money. Why not? If you have money on the side, I don't know, if you spend, we spend a lot on compute, obviously, but the compute expense of a company is usually a fraction of the revenue, right? If your company is very small, even your compute for you is a lot of money, right? Let's assume you spend $10,000 a year on compute. If you could save 18% of that, that would be almost $2,000. That's a hell of a Christmas party, right? So think about it. Then the thing I said earlier about saving electricity and saving cooling and all this is true, right? We all should look at that. Don't fucking Bitcoin mine the shit out of things, because that destroys everything. The real reason why I want you to use Graal is I want you to find bugs, right? We are one, or I think still the only very big company that uses Graal in production. And oh, yeah, I haven't mentioned this before. The tweet service, the social graph service, the, what is it called, the user service, right? And about 20 other very big services, and big I mean in terms of instance size, are running on Graal, 100% on Graal in production at Twitter for over 2 years, right? So every tweet you've seen in the last 2 years was served to you by code compiled by Graal. And we never crashed, never. Did you lose any tweets? I didn't. You wouldn't even know if you lost one, but I'm telling you, you did not. Right, because I mean, that's the funniest thing, that's the cool thing about our business is, if you tweet and your tweet is not posted, you think, oh, I hate my fucking, cell phone provider. Wi-Fi is shit. It was never us. It's great. I know I'm out of time. How much am I really out of time? I have a few more things to say. All right.
I've been asked to be strict with time. A big round of applause, everybody, right, with Chris. Thank you.
Thank you. Thank you.